Okay, today's class activity. So again, go read chapters 9, sections 5 through 7. Go read them in detail to make sure that you're understanding the concepts as good as you can so that when we're working on these, you can apply those concepts. Okay, starting with concept question 13. Go take a look at concept question 13 and try your best to solve that one. Okay, so what's the main idea? We have a car traveling, slams on its brakes and comes to a stop. So its velocity's that way, the acceleration's that way, comes to a stop. Where'd that kinetic energy go? Right, you could say that the slowed because of the friction on the road. That's what hitting the brakes is for. But there'd be a flaw with that, in that the friction can't do work on the car. And so what's best to say is that the kinetic energy turned into thermal energy through friction. And that's because the road is part of the system. Because the road heats up, as does the rubber on the car wheels. And so the kinetic energy went to thermal energy. An increase, it went to an increase in the thermal energy of the system. Okay, so the main ideas with thermal energy is that the two objects interacting via friction are part of the system, and therefore you have a rise in thermal energy of the system because of that interaction. Okay, on to 14. So take a look at that. Think about the concepts you read. Okay, with this one, we've got power. And we've changed the power. We're saying that a crane is able to use a power P to lift a steel beam. And now what power would it be if you lifted the beam twice as far in half the time? Okay, so let's think. Power is defined as a force times a velocity. In this case, we can just do F times V because the force would be up, the velocity would be up, and they're in the same direction. And so we get a positive and no cosine of theta. The theta is 0 and cosine of theta is 1. So if we call this our original power for the original force and the original velocity, then our question is, what is the new power if it goes twice as high in half the time? Okay, now that sounds to me like a velocity, a distance over time. And so it seems like the velocity has increased because it's going twice as far in half the time. And so we have some force, a new one, okay? Maybe I'll put a 1 here to make a difference. So some force, we'll figure out what that is. And we have a new velocity, which would be v1. And we could say v1 is going to be the distance, which is twice the vertical distance. I'll put a delta y 0. Twice the distance in half the time. Okay? Half the original time. Okay, well, that indicates that I've got this force times 4 times the initial velocity, because this is my initial velocity. Okay, so I get a 2 over 1/2 gives me a 4. The last question is, well, how does the force change? Does that mean I'm doing a bigger force? Okay. The problem's a little vague on this, but I think it's sufficient there to assume that the velocity is constant during this time. Cranes don't usually accelerate things up. They usually pull them up at a constant speed. And so if the speed is constant, in either case, in this first case or in the second case, then what can you say about the force the crane is using? So if we think about a free body diagram, here's our beam as a dot. The crane's pulling up with some force. Gravity's pulling down, and if it's moving at constant speed, those should be the same. Whether it's going fast or slow, the force is the same. Now, it'll take a greater force to get it up to speed, but once it's moving, it'll be the same speed as force of gravity. So, or same magnitude of force as the force of gravity. So this is going to be the same thing as F0 for V0, which means our power is 4 times the original power. So this is, again, recognizing proportionalities, but with a little bit more depth of recognizing that the forces were the same because of constant velocity, and that the velocity increased 4 times. All right, that's it for that exercise. Okay, let's go ahead and look at now exercise 35. Go take a look at that and try to apply what you've read to this one. Okay, so with this one, we've got a boy going down a water slide. I'm going to represent the boy as circle there. And it has the boy has an initial velocity and a final velocity, which I'm not going to show directions, and because with energy we don't care about directions, okay, or with kinetic energy you don't care about directions. All right, and then we know that the boy goes through a height h. Okay, now the question is how much thermal energy is generated by the boy going down the slide if we know the height h and we know that the boy starts from rest and ends with a certain speed. So how are we going to try and solve that one? What is our fundamental equation to relate these ideas? Okay, that would be the work, our energy equation that's growing now. That's work external equals the change in kinetic energy plus delta E thermal. We can treat the general motion of the boy as a particle, so the delta K can relate its kinetic energy, but we know that the boy and the water in the slide can heat up, so there's also thermal, which means we need to specify carefully what our system is. We say it's the boy and the slide, okay, both of them together. All right, that means we can include this in our system, which means the only thing that's external would be the force of gravity, which is constant, dotted with the displacement, okay, all right, delta S. And in this case, the force of gravity is always down, so the only piece of the displacement I care about is the vertical distance. So that's just mgh then, mg times the vertical displacement. So that's what the dot product does. It only cares about how much of these are parallel. Since Fg is straight down, I can just choose the straight down component of displacement. And then that's going to be equal to K final minus K initial plus delta E thermal. K final is 0, so delta E thermal then is, adding it to the other side, we get Sorry, I was going to say I was not matching my solution. K final is not 0, K initial is 0. Okay, it starts at rest. So we have K final non-zero. So solving for delta E thermal, we get mgh minus the K final, which is 1/2 mv squared. And if you plug in your values that are given in the problem, you'll get 537 joules. Okay, I apologize. Let me make sure this is clear. I accidentally crossed out K final, but it's starting from rest, ending with the speed. So it's K initial is 0, and K final is non-zero. Okay, so the important thing here is recognizing because there's thermal energy through friction, I need to include both objects that are engaging via friction as my system, and then isolate only those things outside of those objects as external. So in this case, it would be the force of gravity. All right, now move on to 37. So go and try and apply some of these ideas with power to problem 37. Okay, so here we have a block of steel that we're pushing with our velocity v, okay, for a certain amount of time. We apply this force F. Right? It is across a steel table, and we're trying to find out what work we must do. Now, first of all, steel on steel means we have a mu k, right? And so the question here, this sounds a little bit complicated because we have a mu k, which means we're going to have a frictional force, and therefore, if we think of energy, we're going to have to consider thermal energy. But we just need to read this question carefully. We're just asking for the work done by this force. We're not trying to find change in kinetic energy for the box or anything. It's just what's the work done. So we just need to focus on work of the push is going to be equal to that push force times the displacement, delta S. Okay? Now the displacement is to the right, the force is to the right. They're constant. The force is constant, so this just becomes F delta S. All right, and we need to figure out now what is the size of the force and what is the size of the displacement. So this is review now to kind of apply previous things to understand what this is. So how would you find the displacement if we know its velocity and that velocity is constant, so no acceleration, and we know how long? Okay, so we can use this idea, S final equals S initial, or in other words, delta S, is equal, or sorry, S final equals S initial plus a V0 S times a delta T plus 1/2 AS delta T squared, but AS is 0, it's not accelerating. We could just call that 0 or say this is delta 0 equals. And so delta S is our V0S delta T, which we know. So we've got that one. All right, we're good. We can plug that in here. Now, what about the force? How big is this push force? We're not told the value of the push force. But we are told it's steel on steel, and it's moving at constant speed. So what would your free body diagram look like? If I draw a dot for my steel box, I've got a normal force, the force of gravity. It's not accelerating up and down, so I expect those to be equal in length. I've got this push force, and it's not speeding up horizontally either. It's not accelerating, which means my frictional force, Fk, ought to be the same. And so we can relate, say, N equals mg, and F equals Fk, and Fk is mu k mg. So we can now say F equals F sub k, which equals mu k n, which equals mu k mg. Okay, and again, I use Newton's second law to equate these two together, and Newton's second law again to equate these two together. So now we have F and delta S, and we can find the work done. We have mu k mg times V0S delta T, and we have all those numbers. You have to look up the mu k in chapter 6. The value is 0.6 for steel on steel, and when you plug in all your numbers, you get 176.4 joules. Okay. This is a good review problem because not only did we use new information, we also had to apply kinematics in a simple way, but we did. And then we had to draw a free body diagram and relate Newton's second law, or use Newton's second law to relate some of these values together. Now this has a part B. And part B says, well, what is the power going on? So power, once we have the work, power is just the work divided by the total delta T. So this is the total work done over the total time. And so you take this number divided by 3, and you'll get 58.8 watts. And watts is the same thing as joules per second, energy per time. Okay. Very good. Now go ahead and move on to 63. Okay, 63, we've got a farmer trying to pull a 150 kilogram bale of hay up a 15-degree incline at a steady 5 kilometers per hour. The coefficient of kinetic friction is given, and we're asking what's the tractor's power output? What's the power of the force by the tractor. Okay, how should you start this one? Okay, I think this one is worthy to draw a full picture, just to get our mind wrapped around it. Here's our bale of hay. We pulled up by this force F. It's moving in that direction. I'll give it a speed v that we're told. It's got a mass that's given, and it's got a mu k there that's we're told, and an angle that it's happening. So here's a nice labeled diagram. It has a frictional force that whole time. So now I'm going to translate those to a free body diagram, which makes sense. Draw it tilted. What would your free body diagram look like for this? Okay, well, gravity's going to pull down. This is the angle that it makes. The angle of inclination is always between gravity and the normal axis, which means it's got a component of gravity normal to the surface and a component of gravity down the incline, which tells us that our normal force, since it's not jumping up and down off the ramp, must be equal to Fgy. And it also tells us, oh, and we have our frictional force, just about forgot that one. We have Fk. And then our pull of the tractor is equal in length to the sum of these two because it's moving at constant speed. F net is 0 in both components. Okay? So now we need to use those axes to find out our unknown values. First, let's figure out what the normal force is so we can figure out what the frictional force is. And from that, we can figure out how big this force has to be. Very similar to the previous problem we did. Okay, so using the y, we have n minus, we've got fg, and that's going to be cosine of theta, equals may, and that's 0. We've got x. That allows us to say n equals mg cosine of theta. In the x direction, we have this pull force, okay, minus the frictional force, minus fg sine of theta, equals max, which is also 0. That allows us to say F equals Fk, which is mu k times the normal force, plus mg sine of theta. Now plugging that in for there, we can write mu k mg sine or cosine of theta, plugging normal force in for there, plus mg sine of theta, and we can factor out that mg, and we get mu k cosine of theta plus sine of theta. Okay, and that gives us now the force. So we had to use free body diagrams to just figure out how big is this force, knowing that the speed of the bale going up is constant and it's not jumping up and down off the incline. Plugging your numbers, you get 1019.4 newtons, which is an intermediate number, so I kept a lot of digits. And our final question is power. What is the power of this tractor pulling up that bale? So power is defined as work divided by time. Okay. But we also showed that you can write it as force times velocity. Dotted, in this case, they're in the same direction, so it's just force times velocity. And we have the force, and we have the velocity, being careful to convert that velocity to meters per second, since it's kilometers per hour. Right? But in doing so, we can plug that in, and we can say this is 1416 joules per second, or again, that's watts, okay, given by the symbol W. So we had to use Newton's laws and free body diagrams to figure out the size of the force, from which we were able to quickly jump and find the power. That concludes today.